Okay, today we'll start talking about the non-expanding 2 to 1 silicate minerals. We have already discussed the expanding silicate minerals. The main non-expanding 2 to 1 minerals are the fine-grained micas and the chlorides. The mica group, the biotite and muscovite, are examples of unweathered micas typically found in the sand and silt fractions. They are primary minerals. The more weathered fine-grained micas, such as illite and glauconite, are found in the clay fractions of soil. These are secondary minerals. Their 2 to 1 type structures are quite similar to those of their unweathered cousins. Their unweathered cousins are the primary minerals, the biotite and muscovite. Their structure very similar. Unlike in smectites, the main source of charge in fine-grained micas is the substitution of aluminum in about 20% of the silicon sites in the tetrahedral sheets. That's very high substitution, isomorphous substitution. And we know that when we have high isomorphous substitution, what does that result in? This results in a high net negative charge in the tetrahedral sheet, even higher than that found in the vermiculites. We have seen how we have very high substitution in vermiculites, but this is even higher. The negative charge attracts cations, among which potassium, just the right size to fit snugly into certain spaces. These are hexagonal holes that exist between the tetrahedral oxygen groups of the two neighboring or adjacent crystal units. Adjacent tetrahedral sheets are therefore strongly bound together by their mutual attraction to the potassium ions in between. When we say snugly, that means tightly, in very tight spaces, so they hold these crystals units together very strongly. The layers in fine-grained micas are therefore, or as a result, strongly bound together, preventing the type of expansion that characterizes smectite clays. So they are very non-expansive. The fine-grained micas are quite, that means very non-expansive type minerals. Because of their non-expansive character, the fine-grained micas are more like kaolinite than smectites. That means if we compare them, the characteristics are closer to kaolinite, which is 1 to 1 non-expanding minerals, than their possible relatives, which are the smectites, the 2 to 1 type, with regard to what? To their capacity to absorb water and cations, and to their degree of plasticity and stickiness. If you remember, we talked, these characteristics are related to the surface area. So if you have non-expansive type minerals, that means they have very low surface area, which means these characteristics will be very low also. The last group of the non-expanding 2 to 1 silicated minerals are the chlorides. In the 2 to 1 layers of soil chlorides, iron or magnesium rather than aluminum occupy most of the octahedral site. If you remember, when we first started talking about the fundamental structure of silicate minerals, we said in the octahedral layer we have aluminum and or magnesium, but also you can have iron, which is very close to the magnesium in size. It also can substitute. In most chloride clays, a magnesium-dominated trioctahedral hydroxide sheet is sandwiched in between adjacent 2 to 1 layers. So adjacent, side by side, next to each other. So that means you have one layer or crystal unit and another crystal unit next to it. In between them, there is a magnesium-dominated trioctahedral sheet. Thus, chloride is sometimes said to have a 2 to 1 2 tetrahedral, octahedral, octahedral. That's why this octahedral is the magnesium-dominated trioctahedral sandwiched between two crystal units. And also because of this, some scientists used to call it also 2-2, which means 2 tetrahedral sheets to 2 octahedral sheets. Chlorides are non-expansive because the hydroxylated surfaces of an intervening magnesium octahedral sheet are hydrogen bonded to the oxygen atoms of the two adjacent tetrahedral sheets, binding the layers tightly together. So the colloidal properties of these chlorides are therefore quite similar. That means very similar to those of the fine-grained micas. Now we will talk about another characteristic of the colloids in the soil, which is the charges. Where do these charges come? The sources of charges on soil colloids. There are two major sources of charges on soil colloids. One, the hydroxyls and other functional groups on the surfaces of the colloidal particles that by releasing or accepting hydrogen ions can provide either negative or positive charges. We'll see how both cases take place. Two, the charge imbalance brought about by the isomorphous substitution in some clay crystal structures of one cation by another of similar size but differing in charge. We already talked about this earlier, but we will talk about it again here. All colloids, organic or inorganic, exhibit the surface charges associated with OH charges that are largely pH dependent. So they depend on the pH of the soil, pH of the system. Most of the charges associated with humus, 1-to-1 type clays, the oxide of iron and aluminum, and allophane are of this type. So you can notice here we don't talk about 2-to-1 dominated by this type of charges. So they are mostly in this type of colloids. Now, first, let's talk about the constant or permanent charges on the silicate clays. Isomorphous substitution could be the source of both negative and positive charges. Again, we have discussed this earlier, but we're just repeating it to make sure you understand this very carefully. Negative charges. A net negative charge is found in minerals where there has been an isomorphous substitution of a lower charged ion, example, magnesium, it's a divalent, for a higher charged ion, example, aluminum. So a magnesium with 2 positive charges takes the place of aluminum, which is 3 charges. So that means we have lower positive charge to neutralize the oxygen negative charges, which means we will have a net negative charge. Such a substitution commonly occurs in some aluminum-dominated dioctahedral sheets. This leaves an unsatisfied negative charge, like I have just said. The substitution of magnesium for aluminum is an important source of the negative charge on the smectite, vermiculite, and chloride clay micelles. Micelles are particles or crystals, the same, they all mean the same thing. Such a substitution is common in several of the important soil silicate clay minerals, such as the fine-grained micas, vermiculite, and even some smectites. Okay, we can have also from this positive charges, like we have seen also earlier. Isomorphous substitution can also be a source of positive charges if the substituting cation has a higher charge than the ion for which it substitutes. In a trioctahedral sheet, there are 3 magnesium ions surrounded by oxygen and hydroxyl groups, and the sheet has no charge. If there is no substitution, no charge. If an aluminum, which is trivalent ion, substitutes for, that means take the place of, one of the magnesium ions, a positive charge results. So a trivalent took the place of divalent. So we have more positive charges than we need to neutralize the negative charges of oxygen. So this will end up leaving a positive charge. In several 2-to-1 type silicate clays, including chlorides and smectites, substitutions in both the tetrahedral and octahedral sheet can occur. The net charge in these clays is the balance between the negative and positive charges. So we saw that we can have positive charges and we can have negative charges. So the difference between which one is higher will end into what type of charge this colloid or silicate clay mineral will have. In all 2-to-1 type silicate clays, however, the net charge is negative. So in nature, especially like in the soils of Jordan, we don't have net positive charge on the clay. We have net negative charge. So the clays are negatively charged. This is why we talk about cation exchange. The cations are adsorbed on these negatively charged clays to neutralize them. So we have net negative charge. Okay, now we will talk about the pH-dependent charges. The second source of charges on some layer silicate clays, example kaolinite, and on humus, allophane, and iron and aluminum oxide, is dependent on soil pH, and consequently is termed variable or pH dependent. Variable because it's not constant. The amount of it changes as the pH of the soil changes. That's why it depends on pH, and we call it pH dependent. Both negative and positive charges come from this source. Just like we saw in the isomorphous substitution, we can have positive or negative charge. The same here, we can have also negative or positive charge, and we'll see some examples. Negative charges. The pH-dependent charges are associated with the hydroxyl OH groups on the surfaces of the inorganic and organic colloids. So they have to be on the surfaces to be exposed for their action. Broken edges of mineral colloids also generate pH-dependent charges. What we mean by broken edges, when you have a crystal formed from so many crystal units or layers, it has to end somehow. It doesn't keep on forever. Where it stops, the edges that are exposed, we call them the broken edges. And that's where we have these exposed functional groups like the OH groups. The OH groups are oxygen atoms, or oxygen atoms are attached to iron and or aluminum in the inorganic colloid. So these two lines indicate this is part of a huge structure, and this is at the end of it, or on the surface of it, we have exposed OH group. And the same thing with humus, the organic, of course, except we talk about carbon built, because all organic compounds are built around the carbon atom. So instead of aluminum or silicon or iron, you have carbon and connected to an OH group. Under moderately acid conditions, there is little or no charge on these particles. So if you have a moderate pH, it's not very acidic or not very alkaline, we will have no charges. It will be neutral. But as the pH increases, which means more hydroxide ions, the hydrogen dissociates from the colloid OH group and negative charges result. So this is the neutral. We have higher pH, higher hydroxide ions. So this hydroxide ion will react with this hydrogen to form water, and this hydrogen left this OH group, leaving behind it a negative charge. The same with in the organic, except it's attached to carbon, but the same thing happens. OH reacts with this hydrogen to form water, then we have a negative charge form. The reactions are reversible. We see the two arrows back and forth. If the pH increases, more OH groups ions or OH ions are available to force the reactions to the right. And the negative charge on the particle surfaces increases. Of course, if you have OHs more, the more the reactions to the right produces negative charges. If the pH is lowered, OH ions concentrations are reduced, the reaction goes back to the left and the negative charge is reduced. Okay, simple. Like we said, we can have also positive charges resulting from these pH-dependent sources. Under moderate to extreme acid-soil conditions, some silicate clays and iron aluminum oxide may exhibit net positive charges. Exposed OH groups are involved always, like in all of them when we have seen, OH is always involved. In this case, however, as the soils become more acidic, protonation, the attachment of hydrogen. From now on, whenever you see the word protonation, that means the addition of hydrogen, the attachment or addition of hydrogen ions to the surface OH groups takes place. So this is a neutral. Now we have acidic conditions, high hydrogen. This hydrogen attaches to OH to form OH2 plus. So we have a positive charge. Thus, in some cases, the same site on the inorganic soil colloid may be responsible for negative charge, high pH, we saw that, no charge if it's a neutral under intermediate pH values, or positive charge, very low pH.